Alright everybody, and in this video we're going to start talking about the different fundamental properties and making measurements within physics. Alright, so we're going to identify different fundamental units of measurement, explain the use in significant figures in a relationship to uncertainty, and explain how different lab tools are able to be used to measure in various quantities. So this lesson is actually going to be split up into 3 videos for my students. The first 2 videos will be posted for everybody else online. Alright, so the fundamental building blocks of the universe are the protons, neutrons, and electrons that form together to create the various different atoms that you learn about in chemistry. The protons and neutrons are in the nucleus of the atom, while the electrons orbit around the nucleus. As you build and combine atoms together, you can create molecules. You can then also add molecules together to basically build everything else, all the way from the cell all the way up to supermassive planets and stars. Alright, so some of the measurable fundamental quantities that we're going to discuss are length, time, mass, charge, and luminescence. Now in Physics 1 we're going to primarily focus on the length, time, and mass, and most of the other units and quantities that we measure are some sort of combination of these three. We're going to talk about charge and luminescence a lot more in Physics 2. Now, mass is defined as the amount of matter that an object is composed of, where the standard metric unit or SI unit is the kilogram. Now, other SI units that we use are grams and milligrams, and the imperial unit is what we call the slug. Now, originally, the kilogram was defined as the mass of a specific platinum iridium alloy cylinder that is kept in the International Bureau of Weights and Measures in Sèvres, France. However, that is no longer the definition of mass, which is why it's striked out. The new definition of mass was formed in November of 2019, and it changed the definition to a kilogram to be based off the fixed fundamental quantity called Planck's constant, which is the smallest possible unit of energy. Now, why did it take 100 plus years from when we figured out what Planck's constant was to use it now to describe what a kilogram is? Well, because now we finally have the technology in order to make accurate enough measurements in the order of measure to measure the masses precise enough for scientists to be happy. So really it just came down to advancing our technology to be able to make the super small precise measurements. So how do we measure mass? Well, we use scales and balances. Alright, so a scale, as we see in the top right corner here, has usually a spring or some sort of mechanism attached to it so that the weight of the object will push down on that spring, and whoever built that scale knows, like, okay, well, if it pushes this amount because of its weight, well, then its mass must be this because gravity is a set value. While a balance, you'll usually have a known mass on one side and your unknown mass on the other, and you try and balance them. So if you have equal masses on both sides, well, then you know, well, the unknown mass must be equal to the known mass side. And we're going to talk about the more precise physics of how those different instruments work in later units. Now, length is the distance between 2 points in space. Now, these could be 2 points that are fixed, like the side of, say, a house. So you can measure the length of that side of the house. Or it could be a point from where you start to a second point of where you travel to. So that's a distance that you travel. All right, so different ways of measuring length or defining, of using length to measure. Two different concepts between how to use length and measuring. Now, the standard unit is the meter, the distance traveled by light in a vacuum during a given time. Now, this is because light is a constant speed in a vacuum. We know in this amount of time it's going to travel this distance. Some other SI units that we'll use besides meters are kilometers and centimeters, and all of the different nanometers, micrometers, etc. Now we will always use the SI units. Now the English units that many in the United States are more used to, feet, yards, miles, and so forth. There are some alternative units you may have heard of in other situations, such as angstroms, which is on the size of the, which is order of the size of atoms, so very small distances, while light years and parsecs are the more astronomy terms to describe very, 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 very large distances. Well, we can also measure length using meter sticks, yardsticks, or tape measures. So we have a predefined definition for what all these distances are, and we can then create other devices that are based on that measurement to say, all right, this is going to be 1 meter, this is going to be 3 meters long, and so forth. We can also calculate length by using the speed of travel in time. And we'll talk about that relationship in our next unit on motion. All right, so time is how long it takes something to happen. Our standard unit, the second, is defined as the hyperfine transition frequency of cesium, which means an electron is transitioning between two energy levels that 9 billion times in 1 second. Now this transition occurs at such a constant rate that we know, okay, so yeah, this is going to be how we're going to define a second, which is why we call it an atomic clock. It's based on this atomic transition of an electron. Some other alternative time units that we'll use: hours, years, minutes, days, and so forth. How do we measure time? Well, stopwatch, clock, etc. Derived quantities are measurable, so some can vary depending on the scenario. Derived quantities are calculated from our fundamental quantities, like volume is the space that an object occupies as 3 dimensions of length: height, width, depth, to create a derived quantity where you have meters cubed now. So our individual quantities were 3 things, all with meters. Multiply them all together and you get meters cubed. Speed and velocity, distance traveled in a given amount of time. You have a speed unit of meters per second. Distance, meters, divided by the time of seconds. So these are quantities that are derived through calculations. And another one, weight, the force of attraction between one object on another, is mass times acceleration of gravity. So kilogram times meter per second squared, so kilogram for mass, meters per second squared, the unit for acceleration, is what we call a Newton, which we'll use as the unit for weight. Now, all measurable quantities fall into 2 categories: vectors or scalars. Scalar quantities are only described by magnitude, or how much they are, like money, how much something is, or time, how long it takes something to happen. Vector quantities compose both magnitude and direction to describe them completely. So a vector that you may have heard of, like acceleration, how quickly something is increasing or decreasing in speed, but also what direction is that acceleration vector pointing. All right, so if you're increasing speed, you have acceleration, and that vector is going to point in the positive direction, the same direction as your speed, while a negative acceleration will point in the opposite direction of your velocity vector, or velocity versus speed as well. So velocity will have both how fast you're going and are you going north, south, east, west. I'll have a directional component as well. Now we do need positive, negative signs to indicate the velocity directions. All right, so this will be extremely important when we do any sort of mathematics, because if you lose the negative, that's going to screw up your math. All right, some examples of scalars and vectors. All right, scalars: distance, speed, temperature, energy, and time. And vectors, examples are displacement, velocity, acceleration, momentum, and force. Now, dimensions are the physical nature of a quantity. All right, we use mathematical expressions to relate these different physical quantities. And we'll utilize space and time as our primary dimensions. All right, so 1D stuff will be stuff either moving left or right or up or down, while two-dimensional space is a projectile that's moving left or right and up and down simultaneously. All right, so we have directions of motion united through time. All right, so that's the end of the first video, and we'll move on to the next video on analyzing that data.